Welcome to the darkest corners of the cosmos where gravity is infinite and light itself cannot escape the hungry void. Today on Black Hole Basics, we embark on a journey to understand the most mysterious and terrifying objects in the known universe. These cosmic monsters have puzzled scientists for decades, challenging our understanding of physics and the very fabric of reality itself. To understand a black hole, we must first look at the invisible fabric that holds the universe together, space and time. Albert Einstein revolutionized our view of gravity, describing it not as a force, but as the curvature of spacetime geometry. But how are these monsters born? The story begins with the death of a massive star, far larger than our sun. For millions of years, a star fights a constant battle between the crushing force of gravity and the explosive pressure of fusion. However, once the star runs out of fuel, the balance is broken, and gravity instantly wins the war, crushing the core. In a fraction of a second, the core collapses inward at a significant percentage of the speed of light, triggering catastrophe. The resulting explosion is a supernova, shining brighter than an entire galaxy, scattering the building blocks of life into the void. What remains is a remnant so dense that if it exceeds 3 solar masses, nothing in nature can stop its collapse. It shrinks past a critical point, vanishing from the visible universe, leaving behind a hole in the fabric of reality. We have now created a stellar mass black hole. Let us examine its anatomy, starting with the boundary known as the event horizon. The event horizon is the point of no return. Once you cross this invisible line, escape is impossible, even for light. Inside this boundary, the escape velocity exceeds the speed of light, meaning you would need to travel faster than light to leave. Deep within the center lies the singularity, a point where mass is compressed into zero volume and infinite density creates chaos. Time itself behaves strangely here. Due to extreme gravity, time slows down significantly as you approach the event horizon boundary. To an outside observer, an object falling in would appear to freeze at the edge, fading away over infinite time. However, for the person falling in, time passes normally, and they would cross the horizon without noticing any immediate changes. As you get closer to the singularity, you would experience spaghettification, where tidal forces stretch your body into a long thin strand. The gravity at your feet would be so much stronger than at your head that you would be ripped apart instantly. Black holes are invisible against the dark background of space. So how do astronomers know they are actually out there? We often detect them by observing their effects on nearby stars, watching gas being stripped away by an invisible companion. As matter falls in, it heats up to millions of degrees, emitting powerful X-rays that our space telescopes can easily detect. Instruments like the Chandra X-ray Observatory have mapped thousands of these sources, confirming that black holes are common in the galaxy. But stellar mass black holes are tiny compared to the giants that lurk in the centers of almost every large galaxy. These are supermassive black holes, containing the mass of millions or even billions of suns compressed into a single object. At the heart of our own Milky Way lies Sagittarius A, a supermassive giant 4 million times heavier than our sun. Astronomers track stars orbiting this invisible point for decades, earning a Nobel Prize for proving the existence of our galactic monster. Some supermassive black holes are active, devouring so much matter that they shoot jets of plasma nearly at light speed. These active galactic nuclei, or quasars, are the brightest objects in the universe, visible from the very edge of the cosmos. Scientists are still debating how these giants formed so quickly in the early universe, perhaps from the direct collapse of gas. To see the unseeable, humanity combined radio telescopes across the globe to create an Earth-sized camera named the Event Horizon Telescope. In 2019, they released the first ever image of a black hole in galaxy M87, proving Einstein was right once again. That orange ring is not the hole itself, but light from hot gas bending around the shadow of the event horizon. The scale is terrifying. This black hole is larger than our entire solar system, with a mass of 6 billion suns. Later, we captured the image of the black hole in our own Milky Way, confirming that these structures are universal. Stephen Hawking added a shocking twist to the story, proposing that black holes are not completely black, but emit faint radiation. In the vacuum of space, particle pairs constantly pop into existence and annihilate, usually leaving no trace on the universe. But at the horizon, one particle falls and while the other escapes, stealing a tiny bit of energy from the whole. This means that over unimaginable timescales, black holes will slowly evaporate and eventually disappear completely from the universe. This process takes longer than the current age of the universe, so no black hole has evaporated yet in cosmic history. This leads to the information paradox. If a black hole disappears, what happens to all the information it swallowed inside? Quantum mechanics says information cannot be destroyed, but general relativity says it is lost, creating a major conflict in physics. Some theories suggest information is stored on the event horizon surface, like a hologram, preserving the data of what fell in. Most black holes spin rapidly, dragging space along with them, creating a region called the ergosphere outside the horizon. Ideally, a civilization could enter this region and steal energy from the black hole's rotation, powering their society forever. Science fiction loves to use black holes as portals, or wormholes, connecting two distant points in space and time instantly. While mathematically possible within Einstein's equations, we have found no evidence that stable wormholes actually exist in our universe. There may also be primordial black holes, created in the Big Bang, ranging from microscopic sizes to massive giants. Some feared particle accelerators might create them on Earth, but physics tells us they would evaporate harmlessly in an instant. The missing link in the family is the intermediate mass black hole, a rare type that astronomers are struggling to find. We suspect they hide in dense globular clusters, formed by the collision of smaller black holes merging over time. When black holes collide, they don't just merge. They shake the entire universe with ripples known as gravitational waves. Detectors like LIGO have heard these collisions, converting the ripples of spacetime into audible chirps that we can analyze. This gave us a new sense. We are no longer just looking at the universe. We are now listening to it. The energy released in the final fraction of a second of a merger is greater than all stars combined. It is estimated that millions of rogue black holes wander our galaxy alone, remnants of dead stars drifting in darkness. While the chances of one hitting Earth are astronomically low, the thought of a silent, invisible killer is truly terrifying. If one entered our solar system, its gravity would eject planets from their orbits long before it swallowed anything. Let's look closer at the accretion disk. This swirling carousel of matter is the most efficient energy generator in the cosmos. While nuclear fusion converts less than 1% of mass to energy, a black hole can convert up to 40%. This efficiency powers quasars, which can outshine their host galaxies by thousands of times, acting as cosmic lighthouses. In the early universe, black holes fed voraciously on abundant gas, growing rapidly during a period called the cosmic noon. Today, most supermassive black holes, like ours, are on a diet, flaring up only occasionally when a gas cloud wanders too close. Occasionally, we witness a tidal disruption event, where a star is ripped apart, creating a temporary flare of incredible brightness. Physicists joke that black holes have no hair, meaning they are simple objects defined only by mass, spin, and charge. All the complex details of the star that formed it are lost, leaving behind a perfectly smooth object of pure gravity. While charged black holes are theoretically possible, they likely don't exist because they would quickly neutralize by attracting opposite charges. Inside a rotating black hole, the singularity might not be a point, but a ring, potentially acting as a gateway. Some mathematics suggest you could pass through this ring without being crushed, emerging into a negative space or another universe. However, the inner horizon is likely unstable, accumulating infinite energy that would vaporize any traveler attempting to pass through it. General relativity also allows for white holes, the reverse of black holes, which spew matter out and let nothing in. We have never observed a white hole, and they may violate the second law of thermodynamics, making them physically impossible. There is a mysterious link between the size of a galaxy and its central black hole. They seem to grow together. The energy from the black hole regulates star formation, preventing the galaxy from making too many stars and burning out quickly. Without these dark guardians, galaxies might look completely different, and life as we know it might not have evolved. String theory proposes that black holes are actually fuzzballs, tangled balls of strings, eliminating the problem of the infinite singularity. Another theory suggests a firewall of energy exists at the horizon, destroying anything before it even enters the hole. These paradoxes highlight that our understanding of physics is incomplete. We need a theory of quantum gravity to fully understand. Scientists are creating analog black holes in labs using sound waves in fluids to test Hawking radiation and other theories. These experiments have shown signs of phonon radiation, boosting confidence that black holes do indeed slowly evaporate over time. Recent studies even suggest black holes might be the source of dark energy, the mysterious force accelerating the universe's expansion. A wild hypothesis suggests that our entire universe might actually exist inside a massive black hole of a larger universe. The mathematics of the Big Bang singularity are suspiciously similar to those of a black hole, hinting at a connection. In the distant future, humanity might send robotic probes to orbit black holes, gathering data from the edge of oblivion. We might even construct artificial black holes, known as Kugelblitz, to power starships and travel to the distant stars. The danger is immense. A containment breach would result in the ship and crew being instantly crushed into nothingness. Life could theoretically exist on planets orbiting black holes, receiving warmth from the accretion disk rather than a star. However, living there would be dangerous, with constant threats of lethal radiation and the risk of falling into the void. From the death of stars to the centers of galaxies, black holes are the ultimate sculptors of our cosmic history. They represent the limit of our knowledge, the point where our science breaks down and the unknown truly begins. As technology advances, the next generation of telescopes will reveal even more secrets hidden within these dark abysses. The James Webb Space Telescope is already hunting for the first black holes that formed at the dawn of time. It has found unexpectedly massive black holes in the early universe, forcing us to rewrite our theories of galactic evolution. We should not fear them, but respect them as essential components of the intricate clockwork that drives the universe. Like a photon skimming the edge, we have brushed against the mystery of the void and returned with new knowledge. What lies at the center? Is it a dead end, a bridge, or something we cannot yet comprehend? The answer awaits us in the stars, challenging us to keep looking up and questioning everything we think we know. To summarize, black holes are regions of infinite gravity, where space and time are warped beyond all recognition. They possess an event horizon, a one-way door from which nothing, not even light, can ever hope to return. They come in various sizes, from city-sized stellar remnants to galaxy-anchoring monsters billions of times heavier than our sun. And finally, they are not eternal. They slowly leak energy through Hawking radiation and will eventually vanish from existence. If you enjoyed this deep dive into the abyss, please support Black Hole Basics by hitting that subscribe button. Let us know in the comments what cosmic mystery you want us to unravel in our next documentary video. Check out these other videos on the screen to continue your journey through the wonders of our incredible universe. The universe is vast and full of secrets, and we are just beginning to scratch the surface of its grandeur. Thank you for joining us on this voyage into the dark. Remember, curiosity is the engine of all discovery. Stay curious, keep exploring, and never stop looking up at the stars. This has been a Black Hole Basics production. Until next time, space travelers, safe journey through the cosmos. Goodbye and see you in the next video. Music swells and fades, credits are rolling now. We appreciate the team of researchers and artists who made this possible. Special thanks to NASA, the European Space Agency, and the Event Horizon Telescope collaboration for their incredible data and images. This is Black Hole Basics, signing off. Thank you for watching, and have a wonderful day exploring the universe.